So up to this point, we've been integrating functions that are simple. We've been integrating functions that you can use the reverse power rule for. So those are functions that could add a new exponent and divide that exponent by whatever that new exponent was. So x integrated to x squared over 2. X cubed integrated to x to the 4th over 4. And then we talked about the difference between definite and indefinite. So definite integrals were integrals that had upper and lower bounds. So a definite integral was an integral that had a beginning and an end point. So that was something that went from A to B. So that's what we called a definite integral. And then an indefinite integral was simply an integral that did not have an upper or lower bound. And if you integrated an indefinite integral, the big difference was that this became your answer plus c. So all of those rules are coming back into play. So a definite integral was an integral in which you had a bound and yielded a number as an answer. An indefinite integral was something that had no upper or lower bounds and could be represented as a, and see this because I used to teach it after 6-1, could be represented as a slope field. It's also represented as a family of functions, and this is the case where you have to add your plus c. So all indefinites will have a plus c. The fundamental theorem of calc helped us solve for plus c, or in the fundamental theorem of calc, if you were given an initial condition, that initial condition you were given acted as your c value. So we've used differentiation in the past. So we had the tricky concept of integrating u to the -1, and we discussed that it's the natural log of the absolute value of u. And then we discussed why it was an absolute value of u. And then here I'm just showing how the derivative of it becomes 1 over u, and why that absolute value matters for u's less than 0. So I don't know what mathematician, maybe it was before FU became a not so nice statement, but in the anti-differentiation U sub world, it's taught as f of u. So whenever you get stuck and you can't think, just think that these are the FU type problems because they're a little bit more work than the other ones. So it says, if the anti-differentiation of f of u du, is that the same as the anti-differentiation of f of u dx? So in the past, we talked about how the variable of integration needs to match the variable within your problem. So what we're going to look at is two examples. We're going to look at an example where we take the integral of f of u du. So f of u is u cubed. So that's like the integral of u cubed du. So the antiderivative of u cubed du is 1/4 u to the 4th plus c. Right? We're okay with that. Now the next one says find the integral of f of u dx. Well, f of u is u cubed. So they don't match. But u is x squared. So maybe I'll try to plug in x squared where my cubed is to at least maybe match my bounds. But a power to a power says multiply. So that's like x to the 6th dx. So then that becomes 1/7 x to the 7th plus c. And if I made this x squared instead of u, that would be like 1/4 x squared to the 4th, which would be x to the 8th plus c. Does the integral of f of u du match the integral of f of u dx? No, even with substitutions and alterations, these two boxes don't match. So what we're going to talk about today is A, which one of those is correct, and B, how do we adjust for mixed variables and variables of integration correctly. So FYI, the correct answer is the top one. And we're going to see why the correct answer is the top one in a minute here. Okay? So you're going to see why you can't just replace a U with a U and expect your work to be okay. Anybody know what we could have done to make it work? Or have a thought? So what we're going to do is the substitution rule. The idea behind the substitution rule is to replace a relatively complicated integral with a simpler one. So we're going to take something complicated and make it simple. This is the reverse chain rule for integration. So this is the chain rule in reverse. So U-substitution is the chain rule of integration. U-sub is the chain rule of integration. So the easiest way to learn how to do this is through examples. We don't know how to take the integral of a square root with a function underneath. So what we're going to do is get rid of the function underneath. So we're going to replace 2x plus 1 with a new variable. So we're going to call that variable u. And we're going to say that u is 2x plus 1. But we previously said you can't just leave a u in there with the dx. So to correctly be able to integrate this in terms of variable u, I need to also change dx to du. Because we said the correct antidifferentiation was for f of u du. So changing the u to an x didn't work. You have to also change the dx to du. So, where do we have du and dx in our worlds? Well, we have them when we take derivatives. That's Leibniz notation. If you take the derivative of u, that's represented by du dx. The derivative of u with respect to variable x is du dx. So the derivative of 2x plus 1 is 2. So u is 2x plus 1, du dx is 2. Now the goal of my problem is to solve for du and replace dx with du. So what we're going to do is multiply both sides by dx. So we get du is 2dx. We have to divide by 2, so dx is isolated. So du over 2 is equal to dx. And now we're going to substitute, hence the name Substitution Rule. You're going to substitute 2x plus 1 with variable u. And you're going to substitute dx with du over 2. So do you see how I'm directly replacing in my problem? 2x plus 1 is going to become u. And dx is going to now be in terms of du. So my integral is going to go from complicated to simple because it's going to become the integral of the square root of u times du over 2. But what do we know about a constant? Well, that du over 2, that 1/2 can come out in front. So it's kind of like the integral of the square root of u du. And now we're back to simple antiderivatives. So you get 1/2. Square root u is u to the 1/2, so reverse power rule says you add 1. Divide by your new exponent. And then this time, it's indefinite, so you have a plus c. So 1/2 times 2/3, because dividing by 3 over 2 is really like multiplying by 2 over 3, becomes 1/3 u to the 3s plus c. But did my problem start with u? Maybe. No, my problem started with what variable? X. So I need to do one last substitution and say 1/3 go back to x, so it's 2x plus 1, because u is 2x plus 1, to the 3/2 plus c. So you have to start and end your problem with the same variable. And you cannot integrate unless your bounds as well as your variables match. So you cannot integrate unless your variables of integration match. Questions, comments, concerns before I erase and we go to the next one? Anything unclear of where it came from or how I did it? Okay. So once again, when you're doing these problems, you are looking for the complicated part. So what's complicated is what's under the square root. So I want my square root to be simple. So I make my u value what's under the square root. So in this case, my u value is 1 minus 4x squared. And then I'm going to take the derivative of u. Derivative of 1 is 0. Derivative of negative 4x squared becomes negative 8x. And I already know my dx needs to be over there. So instead of taking that extra step to divide over dx, I'm just going to write it with dx on the other side. You know you're going to multiply it to the other side anyways. That's what we call differentials. We did that a little bit in implicit, where you could say, oh, well, the dx can be over there. So du equals negative 8x dx. If I look at my problem, I replace the square root, complicatedness, with u. So I have the square root of u in my bottom, and then up top I'll notice that I have x dx, and over here my du is mostly equal to x dx, but what doesn't match that's with that x dx that I can't substitute out? What's being multiplied by x dx that's not in my integral currently? Negative 8. So what we're going to do is divide by negative 8. And put it with my du. So that negative 8 is going to get subbed into my problem as well. So now I have the x dx. I got rid of the complicated stuff with u. That fraction or constant being multiplied by the du can always go out in front, because a constant can always go in front of my integral. So we're going to pull that negative 1/8 out in front and replace x dx with du. So everything in blue is what I substituted in. So that integral is really the same as negative 1/8, the integral of u to the negative 1/2 du. So now my variable of integration matches my constant of integration. Now I apply my reverse power rule. So I add 1 and divide by my new exponent or multiply by its reciprocal. Don't forget your plus c. So negative 1/8 divided by 1/2 is kind of like being multiplied by 2. So you get negative 2/8, which is negative 1/4 square root u plus c. But we don't want to end our problem with u. We want to substitute back in x. So we get negative 1/4 the square root of 1 minus 4x squared plus c. All right. Complicated is always what's under the square root. The complicated is always what's under the square root. So in this case, my u value is 1 plus x squared. Take the derivative of your u value. We know there's no 2, so I'm going to move it over to my du. So now I have 1/2 du equals x dx. But this x is to what power? The 5th. Well, that puts a damper on things. I don't have a variable to the 5th. So if I replace everything exactly as it is now, I'd get the square root of u. I'd have a 1/2 out in front. I could take away an x value. So that would leave me with x to the 4th du. So I got to figure out a way to get rid of x to the 4th. Does anybody see a solution to get rid of x to the 4th? Remember, we're substituting. So, go ahead, Bethany, what was your thought?
Would you rearrange the u?
That's exactly what I would do. You're going to rearrange that u. So now u minus 1 is x squared. Well, if I need x to the 4th, how do I get x squared to become x to the 4th? You square it. So now we can get rid of x to the 4th by replacing it with u minus 1 x squared So now I still have to clean that up to be able to use my reverse power rules the way I know them. So I would change square root of u to u to the 1/2. I would FOIL my u minus 1. And then you can distribute u to the 1/2. And remember that when you distribute and multiply a variable times another variable, you add their exponents. So 2 plus 1/2 is 5/2, 1 plus 1/2 is 3/2, and no variable gets the variable. The constant of integration is super important. Don't forget to write your du at the end. And now we're just going to take our antiderivative using the power rule. So u to the 5/2 plus 1 becomes 2/7 u to the 7/2, because you add 1. And when you divide by a fraction, it multiplies by its reciprocal. Minus 2 u to the 3/2 becomes u to the 5/2. So that's going to be times 2/5 plus 2/3 u to the 3/2 plus our infinite c. And then your last step will be to distribute the 1/2 and replace all of the u's back with their original x's. So 1/2 times 2/7 is 1/7. 1 plus x squared, or to the 7/2, minus 2/5, because 1, 2 would cancel. 1 plus x squared to the 5/2, plus 2/3 times 1/2 would be 1/3. 1 plus x squared to the 3/2, plus c. Now you don't have to worry about distributing the 1/2 to the c, because that constant absorbs the constant being multiplied by it. So you always want to leave c as c. You never want to write a number multiplied to it, divided by it, etc. So even though that 1/2 would technically sort of distribute in, c represents this generic constant, so it absorbs the 1/2. So I purposely have been writing c inside and outside of the brackets and wanted to touch upon that because it really doesn't matter where you put it. You just want to make sure you never actually add a constant multiplied to it. So that is all of the substitution with c values. We're also going to look at substitution with numbers. So I want you to take your 4-minute break now, because this is kind of like the best pause point as we transition. The upper and lower bounds don't change the process of the problem. The upper and lower bounds don't change the process of the problem. It is merely a way of integrating like we did before. So there are actually 2 ways you can do this. There is the method where you change the bounds, and there is the method where you don't change the bounds. And we are going to look at both. I think yes, I'm coming back to them, but this problem relates to the front one, and I think I just accidentally stapled your papers together in the wrong order.
No, it was on the same page as the
Was
last one
it?
we did. Like the last one we did was example 3, and then 4 and 5 are 6.10.
I don't know if I know where those ones went.
It's like x cubed cosine of x equals.
Like this one. Do they have bounds though?
No,
Okay.
that one. Those two.
But those have, mine have bounds.
Oh yeah, ours don't.
Okay. I think I just meant to delete them. And maybe when I didn't,
No. Yeah.
like, do you know what I mean? I think I just meant to delete them. Because I changed your notes to fit into one day.
Mm-hmm.
So this example here, right? This is the very, very first example we looked at. But what's the difference? Now it has a bound from 0 to 4. This was the very, very first example we did. And our answer was 1/3 the square root of 2x plus 1 cubed plus c. So if it has bounds, you drop the plus c and you evaluate from 4 to 0. So you could take that answer that we already got, remember, the square root cubed is the same as 3/2. So 2 times 4 is 8. 8 plus 1 is 9. I wrote it as a square root because in this case, I would take the square root of 9 first, because the square root of 9 is 3. 3 cubed is 27. And then 27 divided by 3 gets me right back to 9. 2 times 0 is 0. 0 plus 1 is 1. 1 to the square root, 3/2, etc. is still 1. So you get 9 minus 1/3. So that's 8 2/3. Or if you kept it as a improper fraction, that's 26/3. And if you didn't distribute your 1/3, you could have actually had 27 minus 1, which would also have gotten you 1/3 times 26. So there are a whole bunch of ways you can get down to the exact same answer. Now, what if I did this problem all over again with U-Substitution, and I did what we call change the bounds? So you'd start your problem exactly the same. You'd say u equals 2x plus 1. You'd say du equals 2 dx. And then you'd say, okay, that's 1/2 du equals dx. So all of that is the same from before. But now, I'm going to get rid of u to the 4th for my upper and u to the 0 for my lower by replacing my upper and lower bounds with bounds related to u. So that's like 2 times 4 plus 1, which is 9, and 2 times 0 plus 1, which is 1. So I'm now going to integrate 1/2 from 1 to 9 of u to the 1/2 du. And the reason I'm changing my bounds is so that at the end of the problem, I don't have to go back and replace my u with x. So if you have a definite integral with U-Substitution and you change your bounds, you do not replace the u with x at the end. You get your number. So this becomes 1/2. U to the 1/2 becomes 2/3 u to the 3/2. bounded from 9 to 1. 1/2 times 2 cancel, and you get 1/3 u to the 3/2 bounded from 9 to 1. Now you just plug in your upper and lower bounds, and you get 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. And again, 9 to the 3/2 is 9, or 27 divided by 3, which gets you to 9, minus 1/3, which gets me to 26/3. Does that make sense? So do you see how if you want to solve the problem by changing your bounds, you don't have to replace u at the end? Let's do another one. Okay, so this time we're going to only do this problem changing my bounds. The complicated stuff is the stuff inside your parentheses or inside the chain rule. So what's my u value? What's u going to be? Perfect. The derivative of u? Yep, -5 dx. Is there a -5 with the dx? So we're going to divide both sides by -5. So I have a constant -1/5 du equals dx. And then we're going to change our bounds. So you're going to find u of 2. And you're going to find u of 1. So my upper and lower bound get replaced with -7 and -2. So my integral with u sub becomes -1/5. The integral from -2 to -7, u to the -2 du. And it's u to the -2 because I had 1 over u squared, and I just brought my u squared up as a negative exponent, so I could do my reverse power rule. So you get -1/5. You add 1, so you get u to the -1 over -1. Bounded by -7 and -2. A negative times a negative is a positive. So we get 1/5. And then that's really like 1 over -7 minus 1 over -2 So then you get 1/5. We're going to get a common denominator, so you're going to multiply by 2 over 2. So you get -2 over 14. And then a half minus another half becomes a positive. And then to make that in terms of 14, you'd multiply by 7 over 7, or get 7/14. So 7/14 minus 2/14 is 5/14. Oh, how nice. 5/14 times 1/5. Goodbye, 5s. And we get 1/14. So anybody want to see it without changing the bounds, or do we like changing the bounds?
You think it's easier to change the bounds?
I think it's easier to change the bounds. I think you make less mistakes changing the bounds, because all of that multiplying that we did changing the bounds over in green on the side, you would be doing in your problem if you replace it back to x and don't change the bounds. So like that 3 minus 5 times 2 would have been in the denominator of your fraction. So I think by changing the bounds, it takes some of the algebra mistakes we make away. Okay, so here's my trig ones. Are these on the next page, or do you have to flip backwards now? I'm sorry. My slides were just out of order. I think I wanted to match the trig to the trig, and I never copy and pasted your notes to match it. Sorry, guys. So turn back a page in your notes. My thoughts and my work didn't match. What's the u value going to be in this case? When we did chain rule for cosines and sines, what was the complicated part of the chain rule? Perfect. It's the x to the fourth plus 2. It's the inside. It's the angle. So the derivative of that is not 3. It becomes 4 x cubed dx. What's my extra part?
4.
Yeah, so you just got to divide by 4. So you pull out your constant 1/4. X cubed dx gets replaced with du. X to the fourth plus 2 gets replaced with u. And we get cosine u du. Antiderivative of cosine. The derivative of what is cosine? Derivative of sine gets you cosine, so antiderivative of cosine is sine. So it's 1/4 sine u. Now this one's back to c because there are no bounds. And then my final answer gets my u back to an x. So it's 1/4 sine x to the fourth plus 2. This looks really close to its normal rule, but we can't have a 2 inside there. So I got to change my 2 theta to u. So you get du equals 2d theta. So that 2 is the extra part. So you have 1/2 the integral of secant u tan u du. And now, if you go back to your handout, the very, very first page, I gave you like all our rules again. You'll notice that secant u tan u du is just the trigonometric formula for secant u. So this becomes 1/2 secant u plus c, and we don't want that u, we want 2 theta. These are starting to click, right? It's making sense. You can see why it works. Okay? The rules don't change if you bound a cosine problem. And honestly, I think changing the u's on the cosines are the big helpful parts, because I think the trig bounds confuse us a lot. I think we have a tendency to forget them. So changing them kind of takes away some of that stress. So the angle of the trig function is always the u. The angle of the trig function is always the u. So that makes my u in this case what? Perfect. That makes my du and then what's the extra part? So you take out your 1/2, that's easy. Now changing my bounds, u of square root pi squared is kind of nice, right? So the u of square root pi becomes the square root of pi squared. Well, what happens when you square a square root? Yeah, so that makes my new bound pi. And the u of 0, well, 0 squared is still 0. So my bounds become 0 to pi. And then this becomes cosine u du. Because that had x dx in it. And you know multiplication is commutative. So that x dx, even though they're not side by side in the problem, you could just rearrange the terms so that they substitute out together. So even though like in that setup, they're not side by side, we know that multiplication allows me to change the order, thus moving that x to be with the dx. So we get 1/2. The antiderivative of cosine u is good. And then my bounds are pi to 0. So you get 1/2 on the outside, and you get sine pi minus sine 0. Well, the sine of pi and the sine of 0 are both sine of pi and sine of 0 are both 0. 1/2 times 0 is 0. Don't you love when you get an integral of 0? Probably not. But it should make sense that your integral is 0. Think about the cosine from u to pi. What's above and what's below the cosine from u to pi cancel. So the area above minus the area below, 0. Area above, area below, 0. Okay, same idea. My u of my trig functions is always the angle. So in this case it is pi t. The derivative of pi t is pi. Remember, pi is like a number. So if it was u equals 3t, you would tell me the derivative is 3. So the derivative of pi t is pi. So pi is still like the constant that doesn't belong. So we factor, divide it by 1/2 and pull it out. Sorry, divide it by pi and pull it out. So you got 1 over pi. And now we're going to find my u with respect to 1/2 and 1/6. So it becomes pi halves and pi 6. So changing my problems to u's, you get 1 over pi, pi to the 6 to the pi halves, cosine u, cotan u, du. Antiderivative of cosecant cotan u is cosecant. Now this one's a little bit tricky because it has a negative. So you get negative 1 over pi, cosecant u evaluated from pi halves to pi 6.
Where are you getting the data?
The antiderivative. So if you think about the derivative of cosecant is negative cosecant cotan. So since the integral doesn't have that negative, the antiderivative gets the negative. So like if you were to take the antiderivative of sine, it has to become negative cosine because the derivative of sine, the derivative of cosine is negative sine. So you have to add that negative. So anytime you take an antiderivative of a trig function that usually has a derivative with a negative, its antiderivative gets the negative. That was a mouthful. What is the cosecant of pi halves? And think about cosecant as the sine. So it's the sine of pi halves. Sine of 90? 1. So cosecant of pi halves is 1 over 1, which is still just cosecant of pi 6 is kind of like the sine of pi 6. So the sine of pi 6 is what? Yeah, it's 1/2. So then the cosecant of pi 6 becomes 2 because it's 1 over 1/2. So you get negative 1, but negative 1 times negative 1 over pi gives a positive 1 over pi. If you have multiple trig functions, you can actually, in this case, make your u value a trig function. So if we have multiple trig functions, my u value becomes a trig function because the angles of trig in this case are easy. So we're going to make cosine, the stuff being squared in the denominator, my u. That makes the derivative of cosine so the negative goes with the du. So you get negative 1 out in front. And then this becomes, if you change your bounds, u of pi thirds, u of 0, which means you need the cosine of pi thirds, which if the sine of pi 6 is 1/2, the cosine of pi thirds is also 1/2. The cosine of 0 is always ooh, I'm feeling a unit circle quiz. We should be able to spit these out. Cosine of 0 is 1. So then you get negative 1. The integrals change from 1 to 1/2. And then sine u got replaced with du. Cosine theta is u to the negative 2. So that's negative 1. U to the negative 1 over negative 1. From 1/2 to 1. Negative times a negative is a positive. So you get 1 over u from 1/2 to 1, which is 1 over 1/2 minus 1 over 1, which is 1. Now, you didn't have to do this problem with a u. What could you have done? So again, we know that there's multiple ways to do everything. In the past, when we had chain rule, we said, oh, you could also FOIL. Sine over cosine is 1 over cosine is secant. So this is actually u to the pi thirds of tan theta secant theta d theta, which is one of our trig rules, which is actually 0 to the pi thirds. So if you brought that down, and integrated it, then that became secant u from pi thirds to 0. And again, you would have gotten 2 minus 1, which is 1. So it's all about being able to see what you see. If you couldn't see that that became tan secant, which I didn't expect you to see, you can see that there's an alternative way to do it using U-sub. So that's the whole kind of idea behind calculus. There's always a way to do it, and everybody might do it their own way. So we're going to conclude with looking at exponentials. These are like the easiest U-subs you can do, because we know the antiderivative of e to the u is e to the u. So all we're taking into account with our u values is that value or the number that doesn't fit. So when we do an e to the u, anything that is the power of e becomes your u. Whatever the e raised to becomes your u. Take your derivative. The value on that e is going to be what doesn't match, so you divide it by your 5s. So you get 1/5 the integral of e to the u du. And what's really nice is the antiderivative of e to the u is e to the u. So you get 1/5 e to the u plus c. But u is 5x. So you get 1/5 e to the 5x plus c. So, as I said, the e to the u, whatever e is raised to, is always your u. So you don't even have to think. U is sine theta. Derivative of sine is cosine. And then you go from there. So you get the integral of e to the u du, which is e to the u plus c, or e to the sine theta plus c. Nothing extra. Okay? U is equal to the square root of x. Derivative of u is equal to 1/2 x to the negative 1/2 dx. So hence the fact that there is a square root in the denominator. What doesn't match is the 1/2. So you divide by 1/2, which is the same as multiplying by 2. So you get 2 integral of e to the u du, or 2e to the square root of x plus c. The process for natural log isn't much different. Whatever's inside your ln is your u. So, including, however, your ln. So it's the inside and your ln, because we have that x in our denominator. So if you only make it the x of the ln, then you're not going to be able to get rid of the x in your denominator. So we're going to say u is the natural log of x. So its derivative is 1 over x dx. And I could think of that original as 1/3 in front of that problem. So that here's my 1 over x dx. And then here is my ln of x. Oh, I forgot to write my x. And you can see how everything is replaced with u's. So the antiderivative for this becomes 1/3 the integral of u to u, which is our most basic power rule. So it's 1/6 the natural log of x squared plus c. So just like sometimes my u is trig, sometimes my u is ln. I know we're doing a lot, but I lose you for like multiple days. Okay, last few examples. E to the x plus 1 in my bottom and e to the x up top. Thoughts on what my u should be? What's the complicated stuff? The stuff in the bottom, right? That's the part you can't break apart. So you want to make your u e to the x plus 1. And if you make your u wrong and you take du and it doesn't work, like, you could keep trying. But what's nice about this is the derivative of e to the x is, yeah, so then now it's e to the x dx, which is this stuff up here. And then that's my u, so everything's gone. So your integral becomes 1 over u du, and whose antiderivative is 1 over u du. Now ln. And don't forget your absolute values that we talked about at the very, very beginning. And as I talk about it, I write parentheses. So all ln's have absolute values when you take your antiderivative, because we never know about what the sign is. The next couple examples are all of the same. They just have bounds. So you would do everything we do the same, but with bounds. Yeah, you're 5 to the 2x. So then we have our 5 to the 2x, which again, the rule doesn't change. I told you for ease, the exponent is always your u. Same with a number, because e is really a number. So u equals 2x. du equals 2 dx. So you get 1/2 du equals dx. So we get 1/2 the integral of 5u du. And again, we talked about this antiderivative a couple days ago, but the antiderivative of a to the u is a to the u over ln a. So this is like 1/2 a to the u over ln a. And don't forget our constant of integration c. And u is 2x. So we get 1/2 multiplied by the natural log of 5 times 5 to the 2x plus c. And if you wanted to put the 5 to the 2x on top, you could. So you could say like 5 to the 2x over 2 ln 5. That's the same thing. For the u's with the e's, I would change my bounds. So I'm going to show it to you. I would change my bounds the exact same way I did before. I would identify my u, find my du, change my upper, change my lower, and then antiderive with my changed bounds. So if you're in classroom tomorrow, because you're not taking your mock, you'll have class time tomorrow to be able to work on all of this. Or if you're at your dentist.
Me crying. I hate the dentist.
Really?
With everything in me. They always come at me with that scraper and my gums are bleeding and I'm like, really? This is what they say.
So your assignment is up there on the website. This part here and that part are all just the odds. So like don't do 17 to 43 all. It's the odds.
Okay.
Like, does that make, like, I guess I could even type that so it's much more clear.
Good.
And on that page, I'm actually going to put the textbook up for you. So, like, if you don't have your book with you or whatever, I took pictures of the textbook page. So you could actually, 6.2 textbook, there you go. So the textbook is already added to the Fusion file, so if you need the textbook, it's on there as well. You're very welcome. Yes, it's the worksheet that follows in the packet. It's a circuit. So what I like about this circuit is you kind of know you have to find it. I put a ton of space because some of you write big. So, and I don't think, did I two-side some of it? Maybe?
Yeah, they're all two-sided. The 3 pages with 2-sided circuit.
Okay.
And then, are we doing this?
No, so just the circuit in the textbook.
Okay.
The last page is what we're going to do like kind of together on Monday. It's like a little like re-collaborate or whatever. The circuit might be the last page and then those pages are in the middle.
Alright.
But like it's the circuit and the textbook.
Okay.
Yep, just the circuit and the textbook.